In this section, I'd like to explain the solving linear ordinary differential equations using the Laplace transforms. A linear initial value problem of a differential equation with a constant coefficient is given by this equation's nth order differential equations. So a sub n minus 1, a sub 1, and a sub 0, constant coefficient. Initial value problems, initial condition are given y0 equal y sub 0, y prime 0 equal y sub 1. N minus 1's derivatives is at the t equals 0 is a y sub n minus 1. Using this initial condition, we'd like to determine the function of y. To solve these equations, we applied Laplace transforms in the equations. So Laplace transform in the both sides of the equations. Laplace transform of y, the lower case of the y is changed to become the capital Y. Okay, this is the Laplace transform. And the function of s. And the Laplace transform of the a sub 1 dy dt. A sub 1 is a constant values. It becomes a sub 1 Laplace transform of dy dt. This is the first derivatives. So a sub 1, this becomes, using the initial conditions, y0 plus s ys. Using the Laplace transform of a derivative of functions, you can write the Laplace transform of the a sub 2 second derivatives. It's gonna be a sub 2's Laplace transform second derivatives of y with respect to t's. Then this becomes a sub 2's minus y prime 0 minus s y0 plus s squared Laplace transform of y, and it's a function of s. So in general, Laplace transform a sub n, nth derivatives y with respect to t is a sub n can move outside of the Laplace transforms because a sub n is constant values. Then Laplace transform of the nth derivatives is given by s to the n Laplace transform of y minus s to the n minus 1 y0 minus s to the n minus 2 y prime 0 minus blah 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 up to the y sub n minus 1's derivatives at t equals 0. So we can substitute this quantity into the equations. Then it becomes this equation. So this corresponds to the Laplace transform of the a sub n, nth derivative of y with respect to t. And the second term is n minus 1's derivatives. Then g is a Laplace transform of the right hand side of the equations. This is correspond to the gs. Then you can obtain this equation. You collect all the terms related to y. So this is ys, this is ys. Then it becomes ys times a sub n s to the n times a sub n minus 1 times s to the n minus 1. So these terms, and the first terms is here and here is here. And then you sum up all the terms to create the capital PS. So all the terms related to initial conditions. You can move these terms is surrounded by the green can move into the right hand side to create the capital Q, this Q. So A sub n, s to the n minus 1, y sub 0 comes from the this term, A sub n, s to the n minus 1, y sub 0. So this is correspond to these terms. And then you collect all the terms to produce the capital Q's. And divided by the capital P, you obtain the equation for the y. Y equal Q over P plus G over P. Discover the Laplace transform of the function y. Y is expressed Q over P plus G over P. In these equations, initial conditions are included. If you go back to this equation, the initial conditions are given inside of the capital Q, y sub 0 and y sub n minus 1. So this is included. Actually, this is wrong. It's a y sub 0. Once we discover the Laplace transform of y, we apply the inverse Laplace transform of y to find the lower case of the y. So y is obtained by these equations. So using the Laplace transforms, we could solve the ordinary differential equations. Okay, this is the end of this session.